Okay, so let's start. So I am Elie Desmond-Le Quéméner from INRAE LBE Narbonne in France. So we are part of the LEAD project. And so this week we organized this workshop on modeling. So you had several presentations with dynamic models, um, more machine learning models, and the coupling of both. And the objective of this last webinar was to introduce some thermodynamics in the modeling. So thermodynamics of microbial metabolism from Gibbs free energy to yield predictions. So the objective of the workshop is to give you some simple tools for the calculation of Gibbs free energies. So I will introduce the Schnoz package from R and some Excel files that are from an article published in 2010. The second objective is to understand when this calculation will be relevant for the modeling of microbial bioprocesses. And the last part will be on the method to predict yield using thermodynamics. I don't know if I will have time to do everything, but we'll see, depending on what we want, how fast it goes. So first part is, I use some recall probably for most of you about thermochemistry. So if we look at aerobic degradation of glucose, we can compute some thermodynamics quantities associated with this reaction. So you have this reaction of 1 glucose reacting with 6 oxygen and giving 6 carbonate plus 6 H plus. And in thermochemistry, we compute what we call the standard enthalpy, standard entropy, and standard Gibbs free energy, which is a combination of the enthalpy and entropy. So to compute this, what we do is we look at the stoichiometric coefficient and at the standard enthalpy of formation. For most of the chemistry, classic, let's say chemistry compounds, people have measured this standard enthalpy of formation, so for glucose, oxygen, carbonate, etc. So it's possible to compute the standard enthalpy of the reaction with this equation, so the sum of the standard enthalpy of formation multiplied by the stoichiometric coefficient. So stoichiometric coefficient is positive when it's negative when it's a reactant, and it's positive when it's a product. So you can do that to compute enthalpy, you can do that to compute entropy, and then you can compute the standard Gibbs free energy. This is for the entropy. So here, for example, if we do that for the glucose, what we obtain is delta G standard is minus 2,604 kilojoule per mole. But it's not the end of the calculation, because what we want is the real Gibbs energy, not the standard. And so there is a correction to the standard Gibbs energy to have the real Gibbs energy. So delta G is delta G standard plus RT multiplied by the logarithm of the product of the concentration with exponent, and exponent are the stoichiometric coefficient. So here we know everything because the standard Gibbs energy, we just calculated it, and the concentration we assume we know. The stoichiometric coefficient we know, R is a constant, so gas constant, and T is temperature. So with all this, we can compute the real Gibbs energy, and for this example, it's minus 2,852 kilojoule per mole. And why is it interesting? Because in the thermochemistry, people show that this particular function, thermodynamic function, is important because the reaction is possible if this delta G is negative. So here it's very negative. So this reaction is what we call favorable. If the delta G is positive, it means the reaction is not possible, and that's what will be interesting for us during all this presentation. We compute the delta G because we want to see if it's negative, then the reaction is possible, or if it's positive, then the reaction is not possible. In fact, this energy, minus 2,852 kilojoule per mole, is like the available work when we, if we want to use this reaction to do some transformation. And just a remark, it's linked with the law of mass action for those who know that, because if you assume that the reaction is at equilibrium, then delta G is equal to 0 in that case. The definition of the equilibrium, it means that there is equilibrium between reactant and products, which means that delta G is neither positive nor negative, it's 0. And then it gives us a relationship between the ratio and product of the concentration and the standard delta G. And that's how we define this K constant that we use in the law of mass action. Yeah, and just to illustrate, maybe I will first illustration to show you how we can compute all this with Excel file, for example. So this is the Excel file I shared. So if you want, you can do that at the same time. So for example, here, so this file, it's an Excel file that comes from an article. I will show you the article. Maybe I can show now, because it will be used several times. So this article, it's an article from 2010, generalized method for thermodynamic state analysis of environmental systems. And in fact, it's a course. I think it's a course that they did a lot of time in Delft, and then they produced an article from this course. And so you have this article, and you have associated to the article Excel file with a lot of calculation. And I used this Excel file to produce my Excel. So here, what you see, you have the list of molecules. So here you have the name, here you have the formula, here you have the standard Gibbs energy of formation and standard enthalpy of formation. So it's equivalent to have entropy of formation and enthalpy of formation, or standard Gibbs energy of formation and enthalpy of formation. Here it's standard Gibbs energy. And so the objective of this sheet is to compute the standard and real Gibbs energy for a reaction. So for example, we want a reaction of the oxidation of glucose. So glucose is consumed, so -1 molecule. There is also 6 molecules of oxygen, so -6. And then you produce 6 CO2 and probably 6 H2O. And so you see, if we do that, so here what I write are the stoichiometric coefficients: -1 for glucose, -6 for O2, +6 for CO2, and +6 for H2O. And when I do that, the Excel, the sheet computes the standard Gibbs energy of this reaction. And then we have also the real Gibbs energy, but here you see that the value is the same because the concentration are all standard concentration 1, not for the proton, but we don't have proton in the reaction. But you see, if you, for example, would change the concentration of glucose, then we don't have the same value anymore. We have a different delta G different from delta G standard. And you compute also at the same time delta H standard. So that's just an illustration. And if you don't know, for example, here, I know that, for example, from 1 mole of glucose, I need 6 mole of oxygen, and then I know that I will produce 6 mole of CO2 because we have 6 carbon in 1 glucose, so this is pretty obvious. But then maybe I don't know how much water is produced. You see that here the first, this line, C balance, H balance, O balance, N balance, E balance, gives a global balance of the reaction. And if you have something different than 0, it means that there is a problem somewhere. Here you see that you have a deficit in H and O, and if I add 6 water, then the balance is fine, and we have this value of the delta G. If you end up at some point where with something like that, it means that there is a problem. You have to balance your reaction before you can compute your delta G. Okay, that was it for this first illustration. And so that's how I computed these values in this sheet. You see that the values are a bit different because in my file I computed glucose plus 6O2 gives CO2 and H2O, but here I did the different reaction with carbonate and H+, but the value are very close. Okay, and now that you remember how to do that, I just want to show you the order of magnitude of different Gibbs free energy for different biological reactions. So you have here a table from one of our paper where you have different energy for different reactions. So for example, here at the bottom, yeah. Here at the bottom, you have glucose plus oxygen give HCO3 minus and 6H plus, and you have this value for the delta G, standard prime, and delta G. So often in the literature in bioprocesses, at least you will find this notation where you have delta G standard with a prime. Delta G, the prime means pH 7, because often the delta G standard are computed for are very different from the real delta G if there are some H plus in the reaction. So people often compute delta G standard with correction for pH 7. That's what means the prime. And here I have also the value of the true delta G, taking into account realistic concentration for all the products and reactants. So you see for glucose, it's more or less minus 3,000 kilojoules per mole when you have oxygen as electron acceptor. But if you have fermentation of glucose to propionate, acetate, lactate, butyrate, you see that the order of magnitude is 10 times lower. It's more or less 300 kilojoules per mole. And if you look at the methanogenesis here, you see that it's 10 times lower. It's minus 20 kilojoules per mole. So you see that you have a very different order of magnitude depending on the types of reaction. And you see that when you have oxygen, we produce a lot more energy. It's possible to produce a lot more energy than if you just do the fermentation. And that explains also why when you have an environment with oxygen, the microbes that are the most abundant are the ones using the oxygen because they have more energy than the other microbes. And so if we want to make the link with the ADM1, so the modeling of anaerobic digestion, so maybe you have seen this type of diagram, maybe with Gabriel. Here is just a scheme of the anaerobic digestion. So you have the composite waste, and then in the model, it's separated it's hydrolyzed in proteins, carbohydrates, and lipids, and then in amino acids, simple sugars, and then we have the fermentation to acids with a final step to acetate, and then from acetate to methane. And in the model, you have also gas, liquid gas exchange, etc. But here we only focus on the biological part. Probably you have seen this type of matrix also. So it's just a summary of all the stoichiometric coefficients in the model, and on the right you have the rates. And yeah, what is interesting, I will go back to the rates later. Here I just make a zoom on one part of this anaerobic digestion where we start with sugars and we produce, for example, here acetate and propionate. And then acetate is used to produce methane, but propionate produces H2 and acetate, and H2 is also used to produce methane. And when you look at the energy available here for the fermentation is quite high, whereas the energy available for the final step is quite low. Just to illustrate, so hydrogenotrophic methanogenesis here, we have 4H2 plus HCO3 minus plus H plus give CH4 plus 3H2O. If we compute everything, so we have the delta G here with the full explanation with all the concentration and partial pressure. And what is interesting is to put out the partial pressure of hydrogen, because you see that the delta G, calculation of delta G is very sensitive to this partial pressure of hydrogen, because you have 4 hydrogen for 1 methane. And then you can plot how delta G change with the partial pressure of hydrogen. And you see that depending on the partial pressure, you have some partial pressure for which the reaction is possible, because delta G is below 0, so you have the 0 here. So here you have delta G as a function of the logarithm of the partial pressure of H2. So it's logarithm 10 here, so it means that it's 10 minus 1 here, 10 minus 2 here, 10 minus 3, etc. So here you have a lot of hydrogen, high partial pressure, and you have a low delta G. But if you go below 10 minus 5, then delta G becomes positive, and it's, according to thermochemistry, not possible to do the reaction. So you see that the energy available for this is low, and it's even lower if you consider low partial pressure of hydrogen. And also the problem with this part, sorry if I go back here, problem with this, so this is the reaction we use, so this transformation from H2 to CH4. And the problem is that it's coupled to other reaction or other microbes that are producing this H2. So if I do the same calculation for example, butyrate oxidation to acetate on H2, and here I compare with methanogenesis from H2. So when I take into account the methanogenesis, the second one, we have this delta G that decrease when the logarithm of the pH2 increase, and we have the opposite for the delta G of the first reaction. So it means that there is a small window where both reactions are feasible, because here you have the methanogenesis with the delta G that decrease with the increase of partial pressure, but you have the here propionate oxidation with the delta G that increase with the partial pressure. And so if you want to have both reaction, propionate oxidation and methanogenesis, that happens at the same time, it means that you have to have partial pressure in between those two values, so 10 minus 3 and 10 minus 5 or something like that. And so that's why here, in the case of anaerobic digestion, it's important to take this thermodynamic into account. Maybe you saw that in the model. The classic way to take that into account is to have an inhibition term, let's say a classic inhibition term. So here you have the rate of, for example, propionate consumption. You have a maximum rate, and then you have a mono-like function with some inhibition term, one for pH, one for nitrogen, and one for the H2 partial pressure. That's the classic way to do it. And in this article from 2019, they analyzed how it changed things if you do the classic inhibition function. Or the classic inhibition function is something like that. So you have just a parameter that makes this inhibition term goes to 0 when you have a high partial pressure. And they compared in the articles these two types of inhibition. So one with the classic inhibition, and one where they take into account the thermodynamic inhibition. And here you have the plot of how it behaves. But there is another article here from 2022 when they did more or less the same, but they use a different parameter for the inhibition term for the thermodynamic inhibition. And they compare here how the two inhibition behave. And you see that the thermodynamic inhibition in blue is much steeper. The function is much steeper than the classic inhibition. The advantage here is that the inhibition function with the thermodynamic inhibition, if you do it like it's done here, you don't need an additional parameter in the model to take that into account. You just need to compute all the thermodynamic terms. And that's what we use to do this analysis. So if you want to go more deeper in this modeling, we have a brand new article. So it was published this week, but it probably will be available, the final version, only next week or week after. In this article, we analyze the acetate oxidation and propionate oxidation with classic ADM1 model or classic, not classic, because in the classic ADM1 you don't have the syntrophic acetate oxidation, but with a classic function, let's say. And we compare how the thermodynamic function behaves in comparison with the classic function. And we show that the advantage of the thermodynamic function is that it removes one of the parameters of the model, so it's better because you have simpler model and it represents well what is happening in the system. Okay, and so now we can just make one exercise to illustrate what I just said. So for example, I take this example, hydrogenotrophic methanogenesis, methylotrophic methanogenesis, and methyl dismutation. So you have these three types of methanogenesis, and we want to evaluate how the delta G of this reaction change with the H2 partial pressure. And to do that, we can use the Schnoz package in R. So probably you have R on your computer. I will open mine. So RStudio in that case. So if you want to try to run it at the same time, you can. And at the end of this small script, we can maybe do an exercise together. So for the moment, I will just explain everything and show you how it works. So this is the RStudio system, and in R, I use a library called Schnoz. The advantage of using that is that you have everything to compute all the thermodynamics, thermochemistry quantity you want. The advantage is that they have up-to-date databases and they update the databases regularly. Because the problem often, if you remember my Excel file, is that if you want to compute all the thermodynamic quantities, you need to have this standard value. And so you can go to the books and look at the value in the book. You have the value in this table with the article of Pierre and Van Loosrecht, but so the Schnoz package gives you all a very, very complete database. So that's the advantage. You have also, what is interesting is that you have this introduction to Schnoz that is very good. I will show you. If you go to the web page, you have a full introduction to Schnoz with lots of examples, and it explains very well how it works. So I put that in the first line of the. Okay, so when you want to use this package, the first thing is to define what they call the setup. It means the default state for your different elements. So for example, here, so reset is just to reset the system if I run some calculation before. I specify the units I want, which in my case is joule for energy units and Kelvin for temperature units, because I think by default it's calorie for units for energy, and temperature I'm not sure, but it's maybe Celsius degree. And then I define the default molecule for my reaction, which would be in that case CO2, CH4, H2O, and H+. What does it mean? It means that the advantage of this package is that it will allow you to also compute all the stoichiometry of the reaction. For example, if you remember when we talk about the glucose oxidation, for example, okay, here if you do the balance of the elements, you can compute that you need 6 O2 and you need 6 HCO3 minus, but it takes some work to do this computation. It's the same for all this reaction. You can compute all the stoichiometry, but you need to do some mass balance to do that. The advantage here is that the package will do that everything automatically. So I specify, for example, that I want the system to equilibrate all my reaction with this molecule, so CO2, CH4, H2O, and H+. And the number of bases molecularly specified are the same number as the degree of freedom. So I have three elements plus charge, so C, O, H, and charge as a degree of freedom. So I can specify, I have to specify 4 molecules for the equilibrium of the reaction. Okay, this is the basis setup. And you see when we do that, it gives us some information, so the formula of the elements, and then the name, the number of the species in the database, the concentration, and the state. So dissolved or liquid for H2. And if we want more information on one specific compound, we can do that. So you see, so if we just do, so we are interested in methanol, for example, and if we just run info on methanol, we get just the identification number in the database. But if I do this info of methanol, I have all the chemical information on methanol in the database. So you have the name, the formula, the state, and all thermodynamic properties of the molecule. And then, if I want to look at a reaction, for example, I do this. So sub-CRT is a way to define a reaction. And if you see, if I just launch sub-CRT of hydrogen -4, I am telling the system that I want a reaction which consumes 4 mole of hydrogen, and I want it to write on a chemical reaction with this, with my default molecule, and you see what it does. -4 hydrogen and -1 CO2 gives 1 CH4 and 2 water. So it's equilibrating my chemical reaction with my default molecule, so CO2, CH4, H2O, H+. So this is my methanogenesis from hydrogen, and give me some information on the thermodynamics. And I can do that for methanol and hydrogen and methanol, my 3 different reactions. So if just to give you, come back to my presentation. These 3 reactions are these 3 reactions. So hydrogen-trophic methanogenesis, methyl-trophic methanogenesis, so it's 1 methanol and 1 hydrogen giving methane and H2O, and methyl dismutation is only methanol transformed into methane and CO2 and H2O. So I want these 3 reactions in my system. And then what I can do is, so here I have specified the reaction, but I didn't specify the concentration. So I can then specify concentration and also state. So for example, for CO2 and CH4, I specify that I want gas state. And for CO2, CH4, and pH, I specify the concentration or the partial pressure. So for CO2 and CH4 minus. So everything is expressed as a logarithm of the concentration or partial pressure. So for CO2, it's -1, which means 10 minus 1 as partial pressure. Same for CH4, and for pH, I specify pH 7. And then I introduce, so this is for my basis species, and then I introduce a logarithm of partial pressure and for concentration of my other molecules. So for H2, pH2, 10 minus 4, and for concentration of methanol, 10 minus 6. And I specify also the temperature. And when I do that, if I do again my computation of my system, you see the output is a bit different from before. Before, when I did the sub-CRT function, it gives me my equation of the reaction, but it gives me a lot of information on thermodynamics, but it didn't give me the delta G of the reaction because I didn't specify concentration and temperature. If I specify concentration and temperature, so that's what I do here. So I want a reaction that consumes hydrogen with partial pressure of hydrogen that I specified before, and with the temperature that I specify, and specifying also that hydrogen is considered to be a gas phase. It gives me this. So again, stoichiometric coefficient in the reaction. So -4 hydrogen gives 1 methane. All the information on the molecule, and you see you have on the right the log act, so it's logarithm of the concentration or partial pressure. And then the output is thermodynamics, and what is useful for you here is this A, which is the affinity. It's the opposite of the delta G. So it means that the delta G here is minus 39 kilojoule per mole. And so here is just a tool to plot the equation. So you see that's the equation of the different reactions we are considering: hydrogenotrophic methanogenesis, methyllotrophic methanogenesis, and methyl dissociation. And then if I want to have this information on the delta G, but with different hydrogen partial pressure, what I can do is just compute this RA affinity for two different partial pressure of hydrogen. And then I know that the variation of the delta G is linear with the partial pressure. And I can plot my how delta G change with the partial pressure. And that's what I'm doing here. And I end up with this type of graph. So you see that you have the delta G as a function of the logarithm of the partial pressure. And you have the heat for the three types of reactions. So CO2H2 is H2 hydrogenotrophic methanogenesis. You have the methyl dismutation, which is the red line, and you have the H2 methyl reaction, that is the orange line. If I go back to the script, what I did is just, so you see, I did the same as before. Sub-CRT is to compute the reaction. And I do that for the three types of reaction: CO2H2, H2 methyl, and methyl dismutation. And then what I did I just created a matrix where I put all the information I need. So if I look at the matrix, first column is partial pressure of H2. So I have two values, one for -7 and one for 0. And then I have the delta G associated for the three reaction. And then I use this two value for each reaction to plot my lines. And you see that methyl dismutation, of course, doesn't depend on hydrogen partial pressure because there is no hydrogen in the. If you look at this methyl dismutation, you have no hydrogen in this reaction, so the delta G doesn't depend on hydrogen, so you have the flat line, red line. And then you see that for the methylotrophic methanogenesis, you have 1 mole of H2 for 1 CH4, and you have this orange line. And for the hydrogenotrophic methanogenesis, you have 4 mole of H2 for 1 CH4. And you see that the blue line is steeper because the stoichiometric coefficient is 4 instead of 1 for the orange line. Okay, that's it. Are there any questions first, maybe before we do the next step? So the next step is to try to compute, for example, it's an exercise. Use for those that are able to run the script, try to compute the Gibbs free energy of reaction for aerobic degradation of glucose, so the same that we computed before, but using the Schnoss package. So what you need to do is to define the basis setup, and then run the sub-CRT function to have the stoichiometry of your reaction and the Gibbs free energy. So I give maybe 2 minutes to think about it. In the meantime, if someone has a question, don't hesitate. So I go back to my script. So when you want to compute the Gibbs free energy for the degradation of glucose, the first thing is to define what would be the basis setup. So first thing we want to reset the setup because we don't want the same setup as before, so we reset. And we define the units, again, I want Joule and Kelvin. And then I want to write what are my basis species. And if you remember before, basis species were CO2, CH4, H2O, and H+, but in this new example, we don't want CH4, for example, because we want aerobic degradation of glucose. We want CO2 because we know that we will produce CO2. We want H2O, we want H+. The molecule that is missing, maybe it's O2, for example, so we can say, okay, I want O2. And then maybe we want to specify that some of the molecules are, just for example, copy this. So I want to say CO2 and O2 are gas. And I can specify some concentration. So for example, for CO2, so CO2, I will take minus 2 is good. Minus 1 is good for O2, H7. And I can define some concentration for my glucose, for example. So this one. And then say, okay, log of concentration of glucose is minus 3, 10 minus 3, for example. No, log concentration is 10 minus 3, so the logarithm of the concentration is minus 3. Temperature is okay. And then I just want to run my function. So if I take the same example as this one, for example, so I want glucose here, and I want minus 1 as a stochastic coefficient. I want a logarithm of activity that I defined before. So glucose is aqueous, so I don't specify the state because by default it will be aqueous, and I specify its temperature. And if we do that, hopefully it works. Yeah. So you see that it gives me, when I run the subCRT function, it gives me the reaction, so minus 1. So what I say is just I want the reaction that consumes 1 molecule of glucose. And it tells me, okay, for 1 molecule of glucose, you consume also 6 molecules of oxygen, and you produce 6 carbon dioxide and 6 water. And okay, well, here you have some information on the molecules. And you have the affinity, and so the delta G is just the opposite of the affinity. And if I want a kilojoule per mole, I divide by 1000 because it's joule per mole. And if I do that, sorry, I have to take my output. So if it's so you see, I define a new variable here, and if you look at this variable, you have different things in it, and what I want is the out, and this is the affinity of the. And then if I look at the delta G, you see we find minus 2,891, so it's close to the value we calculated before. It's a little bit different because here I probably changed a little bit the concentration, so it's a bit different from what we had before, but it's more or less the same. Okay. If you have any question, it's a moment I can answer some question now. We'll go back to the presentation. So the objective was to compute how the value of the delta G of this different reaction change. So again, methane production from different substrate, either H2 alone or H2 plus methanol or methanol alone. So you have this behavior. So it's interesting here that you see that three lines, they cross at the same point. It's a particular case here because, in fact, for example, if you take reaction 2, it's a linear combination of reaction 1 and reaction 3. That's why we have all these three lines crossing at the same point. But it's also interesting because it means that if you try to understand which microbe will get the most of the energy, you see that if you have high partial pressure of hydrogen, so on the right, the lowest delta G will be the one with the blue metabolism, so hydrogen eutrophic metagenesis. And if you are on the right, the lowest delta G, so the microbe with the highest energy, will be the one with methyl dismutation, which means that, for example, the metabolism with methyl eutrophic metabolism is never the better as giving energy in this case. It's either better to have hydrogen eutrophic metagenesis or methyl dismutation. And just to illustrate this, we did this calculation in an article where we analyzed the pathway of some archaea in the gut, and we were looking at the methyl metabolism. And you see that here we plot the logarithm of pH to a logarithm of C-methanol in this graph, and the color shows what pathway gives the most energy. So it's more or less the same as what we see here, just showing the color of the curve that is at the bottom. So you have a blue part and you have the red part, and you have a part in between where all the reactions are more or less equivalent. And what we see is that the microbes, when we look at the ecosystem from the gut, they are all in the places where either hydrogen eutrophic metagenesis or methyl eutrophic metagenesis are the most advantageous. And whereas if you compare with some ecosystem in sediments, they have very low partial pressure, and in that case you find only methyl dismutation. So in fact, in the end, the metabolism, the ecosystem you find is driven by the energy available for the microbes. So when you have hydrogen, then you have hydrogen eutrophic metagenesis, and when you don't have enough hydrogen, you have mainly methyl dismutation. So that's it for the first part. So the next is to make the link between this thermodynamic calculation and also the microbial metabolism and the yield, meaning the yield of microbial growth. So just to come back to the cell, if you look at the bacterial cell, for example, you can make a balance on this cell and consider it as a thermodynamic system. You have some boundaries of the system, and you have some reaction happening inside. You have some substrate coming from the outside to the inside. You have some products, and the cell is synthesizing some biomass, and you have some heat exchange between the cell and the outside. And you can do some balances. For example, here it's entropy balance or entropy dynamic equation of the system. And so if you want to do that, a complete balance of the system, you saw before that it's easy to compute the Gibbs energy of the chemical reaction happening inside the cell, but what about the biomass? Because we didn't talk about the biomass. So in fact, people measured the mean composition of microbial cell. So for example, here you have some example with bacteria, algae, yeast, and you see that, so the composition is here, it's only CHON, but you see that the composition is quite comparable between the different types of microorganisms. So what people do when they want to compute thermodynamics of the biomass, they use a universal formula for the biomass. And this is, for example, the formula used in the article I mentioned before. So for 1 cmol of biomass, you have the formula CH with coefficient 1.8, N with coefficient 0.2, and O with coefficient 0.5. And when you do that, you can then write chemical equation for the biomass, for the metabolism of the microorganism. So, for example, for the aerobic degradation of organic substrate, with Escherichia coli, for example, and glucose. So you have glucose, you have biomass, and you have some bicarbonate produced, and they consume oxygen. You also need a source of nitrogen, so in that case it's ammonium, and you have some byproducts such as H2O and H+. You see that if you want to write this equation, it's not like that's the equation we discussed before, because you have 6 unknown and you have only 5 constraints, because the constraints are linked with the constraint of the element balance. So you can balance carbon, you can balance hydrogen, you can balance oxygen, nitrogen, and charge. So 5 constraints, but you have 6 unknown in that equation. And you see that also I assume that the stoichiometric coefficient for biomass is 1, is by choice. I can choose one of the stoichiometric coefficients in the equation. So I choose this as one, but I still have 6 coefficients. So I need one more constraint to be able to compute all these coefficients. It's not possible to compute them without that. And one of the possible constraints is the thermodynamics. And that's what we will use in the next minute, use the thermodynamics to compute this stoichiometry of growth. Because when we have the stoichiometry of growth, then we have the yield of the biomass, which is very important for modeling in general. Yeah, maybe first. So this type of reasoning comes from early paper in the 80s, where they tried to devise how microbes store energy. Is there a universal thermodynamic efficiency of growth, things like that? So there is a paper, for example, from 1983 from Westerhoff, where he analyzed how anabolism is coupled to catabolism, and this tries to compute thermodynamic efficiency and show that it appears that some microbes are optimized for a free enthalpy converter. It's optimal with respect to maximal output flow, but for other microbes there is no obvious optimal thing. But then with this, it was an interesting approach. But what people criticize later is that if you want to do this, you need to assume mainly the anabolism. So for those, just as a reminder, the catabolism is the action that produce the energy. So for example, glucose plus oxygen gives CO2, it's catabolism. Anabolism is the reaction that produces the biomass. And the reaction that produces the biomass is not easy to write. And people criticize that if you have different types if you write anabolism differently, then this calculation change, and then it's very complicated. Just as an illustration, for archaea, for example, that consume acetate and produce methane. So this is the real stoichiometry. This is what's measured in the experiment. If we want to try to look at catabolism and anabolism, so catabolism is pretty easy because we know that it's just acetate conversion to methane. But anabolism, we don't know. Maybe we say, okay, it uses acetate to produce biomass, and it's like that. And then the efficiency is 9%. But if we compute, if we assume the anabolism is from carbonate, then the efficiency is a little bit different. And it's even worse if you do that with aerobic metabolism, for example, here. So grow some glucose in that case. You have catabolism, that is glucose plus oxygen give H3O3 minus. And anabolism, you can make different assumptions, and you see that the efficiency range is between minus 10% to plus 62%. So that's why this method was not super easy to use, and people propose different strategy to make this computation and prediction of yield with different approaches. So I will here illustrate 2 methods. So prediction from energy transfer efficiency and Gibbs energy dissipation method. All this comes from the article I mentioned earlier, this article. There is also possible prediction from ATP balance. but to do the ATP balance, you need some very precise knowledge of the metabolism, so it's not always possible. So just first to make the link between catabolism, what I call stored energy, and thermodynamics. So if you take the example of aerobic growth and glucose, you always have the same catabolic energy. So for 1/6 mole of glucose, available energy is minus 475 kilojoules per mole. And then you can compute what is called the stored energy. In that case, we don't talk about anabolism. We just look at what happens if we consume the biomass with the same reaction. So biomass with oxygen gives H3O3 minus. How much energy is stored in the biomass? So you have more or less energy very similar to the catabolic energy. And we know that what we want is metabolic energy in the end. That is a combination of catabolic energy and stored energy. This combination is linked with the yield here, that is expressed in this equation. And if you take these two equations into account and you plot this, you can plot this. You can compute this yield. Why that is interesting for us as a function of all the energy, different energy quantities. So you have the catabolic energy, the stored energy, and you have the delta Gx, which is the energy. Metabolic energy that currently we don't know. And you see that we have a relationship between the yield and this metabolic energy. And if we plot, we have something like that. So for aerobic metabolism, the blue line is like that, and for anaerobic metabolism, it's like that. And you see that depending on the metabolism, the result has a different sensitivity to the value, because if you take a first, the yield is quite different, because if you take 400 as a dissipated energy, for example, you have a yield of 0.5 for aerobic metabolism, and you have a yield of 0.1 or below for anaerobic metabolism. And also the sensitivity is very different, because if you go from 500 to 300 here, or maybe it's better in this. No, yeah. Here the yield doesn't change a lot, but here you go to 0.5 to more than 0.6. Okay, and just to the real equation is something like that, and what people show is that if you think about it, and if you look at the literature, you can define values for the metabolic energy, and if you define the value for the metabolic energy, then you are able to compute the yield. And that's one of the methods, how one of the methods works. So the Gibbs energy dissipation, they say, okay, we know that we assume that the energy associated with the metabolism only depends on the substrate, and they give some equation, and the equation depends only on the number of carbon and degree of reduction. And then you can, if you know that, you can compute the yield. That's the first method. So very easy to apply. Another method, just very quickly, is a thermodynamic electron equivalent model. In that case, what they do is they look at the catabolism and anabolism, but the anabolism in that case is more complex than what I explained before. They assume some conversion of substrate to acetyl-CoA, for example, and then some nitrogen source, and they convert that to biomass. And at each step, they assume they have some universal energy transfer efficiency. And when they do that, they are able also to compute some yield that depends on the substrate. And if you compare the two methods, here you have measured yield versus estimated yield with dissipation method, and measured yield versus estimated yield with electron equivalent method. So if the method is perfect, the points are supposed to be on this line. And you see that, well, it's never perfect. We don't expect it to be perfect, but we see that both methods are more or less correct. And in fact, people show that they are more or less equivalent. So for me, the best method is the dissipation method, because it's simpler than the other method. Yeah, and just to illustrate how we can use the Excel sheet to do that, I go back to my Excel sheet. So the first sheet was just about catabolism, but then I have two other sheets, one about glucose metabolism and one H2. And here you can, I just want to illustrate how we can use this method, for the Gibbs energy dissipation method, to predict the yield with this very simple sheet. So here again, you have the list of molecules, you have the formula, you have the standard Gibbs enthalpy of Gibbs energy of formation, enthalpy of formation, concentration. So here you have the logarithm of the concentration. Here, this column is calculated from this column, so you can change here and it will change here. So here I didn't say that before. Here is just the formula of the molecule. So for example, glucose, you see you have 6C12H6O, etc. It's used to check that the element balance is fine in the system. So okay, we'll consider, for example, glucose metabolism, and we want to compute the yield. So first we want to write the catabolism, so same as before. We consume 1 glucose and consume 6 oxygen, and we produce. Alors, I wrote here the anabolism, so I want the same molecule more or less. We want bicarbonate, so I produce bicarbonate, and then I produce also H plus. Okay. So this is my catabolism. We saw that before. We check that the balance is fine, so everything is to 0, so it's good. We have the standard delta G, and then we have the delta G 0, 1. So 0, 1 is because here we assume only a different concentration for pH 0. Then I wrote some version of the anabolism. In fact, here what is interesting with the dissipation method, they called this column anabolism, but in fact it's not true anabolism, and we don't care. What is important is to write an equation where you synthesize biomass here from the molecule available. So either from glucose, or you can write the same with from bicarbonate, and in the end it won't change the final column. And the final column, what you do, it's automatically computed. Here, so you have some calculation here on the bottom with the dissipation method. So this is what I showed in the presentation. This is this equation. So here, if you remember, you have the energy as a function of number of carbon and degree of reduction. So in the Excel file, they compute here this value from the number of carbon and degree of reduction. So they compute dissipated energy. And what they say is, okay, I want to combine this column and this column to have a final metabolic reaction that has this value for the metabolic energy, this value that comes from here. So they do the linear combination of these two columns and gives this final. This is the result of the calculation. And you see, for example, that for 1 mol of biomass, you need so you need 1/4 of glucose, and it gives you the yield. So the yield here is computed from the ratio between this mol of biomass and this glucose. So that's a very practical way to compute everything for the yield with the dissipation method. Here I have another example with H2 metabolism. So it's more or less the same. You see the main difference will be the dissipated energy. So that may illustrate also the question of Sorange. You see that for glucose, dissipated energy is 236 kilojoules per mole, but for H2, it's almost 1,000. So it makes a big difference for this type of metabolism. And then we do the same. So here it's already written, but we write catabolism, we write some anabolism. It's not a true anabolism, but we don't care. And then this column is a linear combination of these two, and we want that to obtain this final energy. And from that, we compute the yield, and in that case, it's 0.02 mol. It's not from glucose, it's mol of H2. 0.02 mol X per mol of H2. And you see, it's very different from glucose. So for glucose, you have 4 mole of biomass per mole of glucose. And here you have 0.02 mole of biomass per mole of H2. Okay. And maybe just to complete. So this, as I said, this Excel file comes from the paper of Claire and van Usrecht. And if you want, I can just open quickly. You have many more different calculations in the. So this is the original file, and you have a lot of different sheets. That all of the sheets correspond to an example in the paper. So box one is you have a box in the paper, and you have examples. So you have all the calculation in the box in these different sheets, and they illustrate different calculation. And for example, what I just the well, yeah, for example, this is an example with a dissipation method. You have, in fact, a comparison between ATP balancing method, dissipation method, and electron equivalent method. And you have the appendix where you have all the standard enthalpy of formation of different compounds. That can be useful, but if you use the Schnoss package, you don't need that. Okay. Yeah, I will maybe finish about the yield, but I will probably skip the part with on the equivalent between Gibbs free energy and electric potential for biological and chemical systems. If you have question on this, you can also contact me. So just to finish this, just a remark on the yield. So we talked about the yield. The yield we predict with the method. And one important thing that people don't realize often is that the yield that is predicted is not any yield, it's the maximum yield. And what is the maximum yield? It's according to the equation of Peart. Yield without maintenance, because if you know the Peart equation will make a relationship between the consumption of substrate. So QS is the rate of consumption of a substrate. And what Peart says that, okay, when you consume the substrate, you consume some substrate for growth. This is what we have here. Mu is the growth rate, and Y is the yield. But you have also some substrate that is used for maintenance for the biomass. Because you don't use all your substrate just for growth, you also use substrate for different things, movement and different things. So it means that depending, for example, in the chemostat, depending on the dilution rate, yield change just because the ratio between the growth and the maintenance is different. So we can compute, for example, here 1 over y as a function of 1 over y maximum. So y excess is a real yield, y excess max is a maximum yield, like in this equation. And then you have the maintenance term, and mu is the growth rate. And you see when we do that, so this equation comes from this equation. It's just when you divide everything by mu, you have QS over mu, give you the yield. You have 1 over y excess max, so stays like that. And then you have MS divided by mu. And which means that if you change in the chemostat, we know that mu will be equal to dilution rate. And so it means that if you change the dilution rate, you change the mu, and then you change the apparent yield. And that's what it's just an illustration here with an example. You see that it comes from experience from chemostat. And here they plot 1 over the yield in gram metanol per gram cell as a function of 1 over the dilution rate. And you have this more or less linear relationship. And the yield, max yield, is what happens at the when 1 over dilution rate is equal to 0, which when the dilution rate is super high. So it's an extrapolation of the yield when maintenance is negligible. So it's important to realize that because it means that in your when you use a method, you predict maximal yield, but then if you want to refine what's your prediction, you need to take also the maintenance into it. And some people try to refine a little bit the Gibbs energy dissipation method by completing the database. So I give several examples here. So this one paper from 2007, and then there is one from 2011, and one from 2018. But in fact, there is often a problem with this refinement, that they forget that what we want to predict is the maximum yield, and so they feed in the database yields that are not maximum yield. So it's not very good for the prediction capability of the method. Just I think in that one it's good, but the next after that it was a problem. Just to illustrate here, in that case, so they change a little bit the way the energy dissipated is calculated, but it's the same as the rate is the same as the Gibbs dissipation method. And you see that the range of the prediction is plus or minus 10% of the yield, so it's good, but you see that you have some problem for some microbes. It's mainly fermentation in that case. Okay. And I will probably skip this. It's just an explanation on how we relate the Gibbs free energy to redox potential. I will maybe just mention that in electrochemistry, the electric potential is directly linked to the Gibbs free energy. In fact, there is an equivalence between potential and Gibbs free energy. It's linked with the Faraday constant, F, and the number of electron exchange in the chemical reaction. So, and then you can relate potential to energy. And that's it. So this is just main references. So this is the Schnoss package and the link to the introduction page. The paper from Claire and von Utrecht. And this paper we just published, I think it's interesting if you want to implement the thermodynamic inhibition, the yield calculation in a classic ADM1 framework, because with the paper, we give the code where you have everything. So you can use it. It's probably not available today, but it should be next week or the week after. That's it. Thank you. And if you have any question, don't hesitate. It can be now, or don't hesitate also to contact me by email.